Assalamu alaikum. How you doing, guys? Today I'm going to talk about the bond anchorage and development length. This chapter actually I have divided up into three parts. Part one, I'm going to talk about the theory behind development length, how we calculate development length, give you a couple examples on that. And then on the second part, we're going to talk about the detailing at the critical section, how we're going to use the development length to do that as well. While in the third part, I'm going to be talking about more examples, splices, and what we call a moment resistance diagram. So let's start with, again, part one, in which we're going to talk about the bond, anchorage, and so if you remember back at the beginning of the class when we started the design due to lecture, we had like 5 assumptions, and one of these assumptions was that we have perfect bond between steel and concrete. And back then I mentioned, well, it is not a perfect bond, but we have to make it so, or there are steps that we are going to do to make this as close to perfect as possible. And this is the section that we're going to talk about that. Where we try to make it as perfect as possible. Again, I said as possible. Now, here I'm just restating that. I'm saying for reinforced concrete to behave as intended, it is essential that bond force develop at the interface to prevent slippage. Okay, so imagine if this steel bar right here, there is no bond in it. And so which means due to the tension force that are developed due to the flexural force coming from P, then we're going to notice some slip between that bar and the surrounding concrete. So what are the factors that influence the bonding? Well, there are 3 of them mainly. One is a chemical adhesion between the 2 materials. The other one is a friction due to the natural roughness of the bars, and here I'm talking about smooth bars, so there's some coefficient of friction, if you will, between concrete and bars, but these 2 are low compared to when we, and I'm going to talk about this in the next slide, we have what we call deformed bars, and these deformations, which are these actually will add some sort of what we call a mechanical anchorage, and that will also increase for the bond between concrete and steel. Okay. Now in the past, as I said, there were no deformed bars and we were using smooth bars. So when the bond strength is broken between steel and concrete, these bars would actually slip out of the beams. I mean, they would literally slip out. Okay, so then people back then thought, okay, so how can I prevent that? And they introduced what we call hooks. Okay, so now these hooks prevent the bars from slipping, but on the other hand, it does not prevent the loss of bond strength in regions like here. So here we have completely cracked concrete. Okay, so this whole tension is carried by the steel, which is typically tension force would be the moment divided by this moment arm right here, so it's going to be M over JD. So that will lead to larger deformation or larger deflection in the steel bar itself, and that will also lead consequently to larger deformations in the beam. Okay, so as you can see, here we have 2 zones, fully cracked zones, and here there's no cracks whatsoever. So this actually could be analyzed more or less like an arch, with my supports being at the hooks. So now that would be now my new structural part, if you will. But again, these hooks really did not prevent the larger deformation or deflections in the beam. So that led us to the use of deformed bars, okay, and it added to the bond strength immensely, and let's say did not prevent, but it delayed the onset of split. So we have actually two types of failures. One is the direct pullout of the bar, and that was synonymous with smooth bars at the beginning. So now the added one is the splitting of concrete along the bar, and that's due to the what we call a wedging action when the ribs of the bar bear against the concrete. To explain this part, if I would like to pay attention to this drawing down here. Here I have a steel bar, which is this one. This is my steel bar, and here's my surrounding concrete. Okay, so if I, let's say, and let me just remove that so you know which one is which. So let's say I'm applying, well, I'm not applying, so due to the flexural force, we're going to have tension forces in the steel bar. So as this is trying to move this way, it's going to start pushing against the concrete, and the concrete obviously is going to push back. Okay, so that force by the concrete on the bar might be something like this. So this force again is pushing on my steel, and on the other hand my steel is pushing on the concrete like that. Okay, so this is concrete on steel, and this is steel on concrete. Okay, so now as you see, this force is at an angle, so this one can be analyzed into two parts. One is a radial part, okay, and the other is a longitudinal part. Right, so this radial part here causes what we call a circumferential tensile stress in the surrounding concrete. So again, since concrete is weak in tension, then that will lead to cracks, and that will lead to radial cracks, and that's going to be actually parallel to the bar along the beam. Okay, so that's what happened to the splitting. So when both of them are overcome, I mean both the pull-out resistance and the splitting, then we're going to have complete failure of the beam. So one of the things that influence direct pull-out, first of all, if I have enough confinement, by confinement I mean the presence of the stirrups, and we're going to see how that's going to play out in the coming slides. Then also if I have a smaller diameter and but with sufficient large concrete cover and large distances between the bars spacing, then at that point I'm expecting to have a pull-out resistance more than I would have splitting. On the other hand, if I don't have insufficient confinement or cover spacing between bars, I mean spacing between bars and the cover, then I would expect to have splitting failure more than direct pull-out failure. Okay, and we will see how that's going to work out itself in the examples. All right. So now let's see what's going on. As I said, I have two types of bond failure. One is the pull-out, and one is the splitting. So if I'm going to talk about the pull-out, okay, so the pull-out is usually attributed to the slipping bond stress. Okay, so if I look here, and this is kind of a cantilever beam. ABC is my steel reinforcement. P is just a force, and then I have two length L1 and L2. Length L1 is kind of anchored in the column, if you will. So this is my column right here, and this is the distance that I'm putting into the column from the main reinforcement here. So if I look at section AB now, and I isolate that reinforcement bar, you can see as I'm applying tension force, I'm going to have in opposite direction the let's say the friction between the concrete and the steel. So if I call this slipping stress, then the force of that will be the circumferential area of the steel, which is going to be pi dB times that length, and that is going to be equal to the tension force which is simply the area of the steel times the yield stress. So that will lead to some, and again, these equations are very simplified equations. They are just to show you how we started with the actual development length formulas that I'm going to present to you in the coming slide. But this is just basics physics, if you will. It is much more complicated than that, but at least it will give you an idea how the that length L1, which in the future I'm going to call LD, relates to the slipping of steel and concrete. So we can notice, first of all, that there is the yield strength of steel. We can see the diameter of the bars involved, and then that slipping bond stress, which we actually don't have accurate information on. So this is from the bond stress. And then we, like we said, because of the presence of the deformation, we also have the bearing stress, right? And we explained that. So now this is my bearing bond strength. Now, again, multiply that by the bearing area times that same length L1 is going to equal, again, also the pi dB squared over 4, which is the area of that steel reinforcement times its yield. Again, you notice that that length, or again, which we in the future are going to call development length, is a function of my yield stress, diameter of the bar, and the bearing stress and the area of the bearing stress. But again, this is very simplified, just to give you an idea. So all of that in perspective, and relate this to the actual moment. So if I'm going to take some section, let's say DD prime over this length, I know that the moment at D is simply the, that the force, tension force at D is simply the moment at D divided by the lever arm, JD, and then TD prime is also that moment MDY divided by the lever arm, which is JD. Then again, if I take the bond strength, do some equilibrium equation, summation of fx, if you will, equal to 0 in that direction, then over the length dz, then we have the slipping bond strength plus the bearing bond strength times that dz will equal to the change in moment, right? Which change in tension force, Td minus Td prime. If I replace Td with Md over Jd and Td prime with Md prime over Jd and divide by dz, then you will see that that bond strength, and I'm going to call this my full bond strength, which is coming again from both splitting and pull out, okay, is going to be equal to the change in moment, right, dm by dz at that section, which is simply the shear. So we can, from that, we notice that my bond force, or flexural bond force, actually is proportional to the shear or to the rate of moment change at that section. Okay, but as I said, these are very simplified equations. They do not provide an adequate measure of safety because we really don't know what they actually look like. Okay, then, and the other thing is, like I said, there is some localized action going on, okay, because again, we have, we said that at the beginning as well, that we have some portion of the beam that are cracked, some of them that are uncracked. So because of that, that bond strength is not quite fully as simplified as I have shown you, okay, and that obviously will lead to the definition, what I call to the development length. So development length is defined as that length of embedment necessary to develop the full tensile strength of the bar, controlled by either pull-out or splitting. Okay, so which means also that the main requirement for safety against bond failure is that the length of the bar from any point of given steel stress Fs or Fy to its nearby free end must be at least equal to its development length. Okay, which means if I at that point right here at point A, if I want to have a full yielding at point A, which was one of the things that we really stressed on during our flexural design, I must have this length beyond that point for me to develop Fy. Okay, so I need that length. So I need to provide this length for me to get full yielding at point A, okay, which is right here. So another thing, so what we did kind of, instead of worrying about what the actual bearing stresses or splitting or slipping stresses are, we kind of said, okay, what is the adequate length that is required for me to get to that point, to that perfect bond. Okay, so this is what we will attempt to do. So that will kind of take away, but at least now when I talk about development length, you will now know why I'm talking about development length and why I'm going to stop talking about both the splitting stress or the bearing stress. It's kind of how I converted that concept into this concept. Okay, so if I'm going to mention some of the factors that influence my development length, obviously the tensile strength of concrete, the cover distance, the bar spacing, again, like I said, these, and transverse reinforcement, these kind of influence or control which type of bond failure I'm going to have, whether it's going to be a pull-out failure or a splitting failure. The one thing actually that is another factor, which is what we call the epoxy. In some countries where rust is a big or a huge problem, we tend to cover the steel with epoxy to prevent them from rust. But this actually leads to reduce in friction, which means that we need more development length, and there's a factor for that, and we're gonna mention that as well. So now this leads me to the provisions of the code, and like I said, most of what's presented at the code, by the way, is based on statistical data. This probably, with more research into this area, is going to change, and it did for some of it. And then I will mention what type of changes we had in this new code. So in this case, so the one that deals with development lengths in the code is section 25.4. And it starts with the statement that the calculated tension or compression in reinforcement at each section of structural concrete members shall be developed on each side of that section by embedment length. And this is our thing that we are going to talk about the most. Hooks, yes, sometimes when there's not enough space for me to put enough length, I can use a hook instead. We call a headed deformed bar or a mechanical device or a combination thereof, which means anything I can use to get that development length in. We will not use hooks or heads in compression. Now, as far as this course is concerned, we will not be talking about the headed deformed bar or any mechanical devices. We will just concentrate on the calculation of the development length and hook. One more thing, the square root of F prime C shall not exceed 8.3 megapascal. So if we have high strength concrete, the maximum you can use is 8.3 megapascals. So now we're gonna have, like I said, you have development length for both tension and compression. Now we're gonna start off with tension, and in that it says the development length, which we're gonna call LD for deformed bars and deformed wires in tension, shall be the greater of A and B, which means whatever you calculate from A or B, you will take the larger of both. Now, B is straightforward. It has to be at least 300 millimeters. As far as A is concerned, there's two ways where we calculate the development length from. One is a more, this is usually by using what I call tables, and this is where we start with a more, let's say, involved equation to calculate that, and then we have some modification factors, and we're going to talk about that as well. Before we get into that, if I have bars with Fy larger than 550 megapascal and they are spaced closer than 150 on center, then transverse reinforcements shall be provided such that KTR shall not be smaller than 0.5D. Now, when we talk about the equation, there's a value that we call a KTR. I'm going to show you how we're going to calculate that. And for this particular one here, it should not be less than the diameter of the bar over 2. Okay. Now, for deformed bars, LD shall be calculated in accordance with table 25.4.3, and this is the table that we are now going to mention. So this is the table, and let's see what we have. So here we have conditions. Here I'm having equation, and here I'm having another equation. Now this is for phi 19 and smaller, and this is for phi 22 and larger, which means 22, 25, 30, 32. So in our country we do have phi 20. I'm usually inclined to use phi 20 with this part over here, based on the fact that it says phi 22 and larger. Okay, so to me, anything less than phi 22 is going to be in this column right here. Okay, so let's start with the conditions. So condition 1, it talks about the spacing and cover. So here we have clear spacing of bars or wires being developed or lap spliced not less than diameter of the bar. So the clear spacing is this. If I have a bar here and I have another bar here, then this is my clear spacing. Okay. So this clear spacing should be at least diameter of the bar. Clear cover, at least diameter of the bar as well. So the clear cover is again from the bottom of this. So if I have a cross section like this, then this is my clear cover. Okay, even if there is a stirrup included, again the clear cover is always going to be from the bottom of the steel bar that I'm about to calculate the development length for. So again, clear spacing, diameter of the bar, clear cover, diameter of the bar, and stirrups or ties throughout LD not less than the code minimum, which means I cannot use, like I said, in the shear, there are some instances where shear reinforcement is not required, but or not needed. But for me to be able to use this equation right here, I have to provide shear reinforcement. Okay, so this first one needs those three conditions: clear spacing, diameter of the bar, clear cover, diameter of the bar, and minimum shear reinforcement. Okay, or so if one of those three is not satisfied, I can look at the other condition. The other condition is telling me that the clear spacing of the bar or wires being developed or lap spliced at least 2 dB and clear cover at least dB. So if I want to forego the condition of shear reinforcement, then that spacing now here has to be at least 2 dB. Okay, so when it says or, it says you can use either the three conditions above or the two conditions down here. Okay, so which means if those conditions are satisfied or one of them are satisfied, then I can use this equation here to calculate the development length. If I'm having a less than phi 22, which is Fy, which is my yield strength, this is what we call epsilon T, which is a psi-t, excuse me, which is a factor for the cover of concrete, and it will be explained in the following slide. Actually, two more slides. Epsilon E is due to what we call the presence of epoxy. Now this one is new, which is the psi-g, which is the influence of the grade of steel. Lambda is, again, because we're dealing with normal weight concrete in this course, it's going to be always 1. Square root of prime c is known, and then dB is the diameter of the bar. Okay, so this is when it's less than 522. If it's more than 522, then we have to use this equation. It's the same, but the only thing that's changing is this factor. Here it's 1.7 is 2.1, which means we're going to have larger development length for larger diameter of the bars. For this case right here, which says other cases, here if you do not want to check whether you have all of these conditions, then you can just run down this table and use this equation right here. Obviously, you can see instead of using 2.1, I'm using now 1.4, which obviously will mean more development length. And this was 1.7 and dropped down to 1.1. Okay, so just to summarize, I have 4 equations for development length, 2 for less than 522 and 2 for more than 522. If I want to use this equation here, I have to satisfy all these conditions that we talked about. If I do not want to satisfy any conditions and I just want to use them blindly, then I just go to the other case part and use these 2 equations right here. Okay. The other equation that we are going to use, which as I said is the more involved equation. Okay. Here, this is the equation that if I do not want to use the tables, and usually this leads to lesser development length as well. So let's look at what we have. Here's again a factor of 1.1, square root of f prime c, cb. This whole term, cb plus ktr over delta b, is what we call a confinement term. Okay, and that is again, like I said, it's going to influence whether we're going to have a pullout or a splitting. So let's go into CB. So what is CB? So CB is the lesser of. Okay. So now I can calculate it from two parts. Part A, the distance from center of a bar or wire nearest to the center. So if this is my concrete cross section, let's say at the bottom, and this is my bar, then the distance that I'm talking about is from this center to the nearest concrete surface, which is this. So it could be this distance or that distance. Okay, so this is for bottom bar. If I have a top bar, same thing. No, the location of the bar is here. This is the center of the bar. And this is the distance that I'm talking about in part A, and this is this distance as well. So it's both the vertical and horizontal distance. Okay, and 1/2 the center to center spacing of bars or bars being developed. So if there is another bar here, so this center to center spacing, okay, and I'm taking 1/2 of that. All right, so whichever is less, this is the one that I'm going to use as CB. And this lesser distance actually is going to control whether the splitting is going to be in the horizontal direction or the vertical direction, and I will show that in the examples. ATR is what we call a total cross-sectional area of all transverse reinforcement with spacing S that crosses the potential plane of splitting through the reinforcement being developed. Okay, so now depending on, so let's say if I have my bars over here, and this is my stirrup. So if splitting is going to be in this direction, then the ATR that I'm talking about is this plus this. Okay, because these are the one that are going to stop the movement of the crack. Now, if splitting is in this direction, then the only ATR that I'm talking about is this. Okay, so here I'm going to have 2 ATR, and here I'm going to have 1 ATR. The ATR being now the area of the stirrup, basically. And again, I will show that more in the examples. So once I calculate the ATR, I can calculate the KTR value, which is a constant 40 times this area, transverse area, divided by the spacing of the stirrups along the length being developed. So if I'm developing, let's say, the bar in this direction, and I have, let's say, stirrups like that, 1, 2, 3, 4 stirrups, then the spacing that I'm talking about is this spacing. Okay, here, that's the spacing. N actually is the number of the bars being developed. So if I'm looking at this case here, the number probably would be 2. 1, 2. Okay. If you don't want to calculate KTR and don't want to go through that whole mess, just assume it to be 0. You can do that as well. Okay. So if you don't want to calculate that and assume it to be 0, it can be done. So let's talk about these modification factors. So the modification factors are, again, we have lambda, which is again for lightweight. And since we are using normal weight concrete, we're only going to use that 1. Then there's the reinforcement grade. And this was introduced new in this code. So if I have grade 280 or 420, then this is going to be 1. In our case, in Jordan, most of our cases we're using these 2 anyway, so it's usually always 1. But if for some instance you needed high grade steel, then this is going to be 1.15, it's 550. For 690 is going to be 1.3. If you have any grade in between, then you just use normal interpolation. Here is my PSI-E, which is for epoxy. Now, if I have what we call epoxy or zinc epoxy dual coated reinforcement with clear cover less than 3 dB or clear spacing less than 6 dB, then I have to use a factor of 1.5. For all other conditions, I can use 1.2. If I have no coating whatsoever, then this is going to be 1. Okay. Size factor, which appeared in the other equation. If it's number 22 and larger, I'm going to use 1. If it's going to be 19, it's going to be 0.8. As I said, I'm lumping in the phi 20 with the phi 19. So on the basis of, okay, 22 and larger. So anything less than 22 is going to be 0.8. The casting position, it says if I have more than 300 millimeter of fresh concrete placed below the horizontal reinforcement, then this development length factor is going to be 1.3, and this is usually applied for top reinforcement, by the way. So if I have a cross section like this, then this distance, if it's more than 300 millimeters, then I need to apply 1.3. There's also a caveat that the product of Psi-T and Psi-E should not exceed 1.7. So if you multiply 1.3 times 1.5 and it's more than 1.7, which I think it is, then you can only use 1.7. Now, moving on to the development length of compression. Compression is a little bit easier than tension because I only have 2 equations to contend with. First of all, the minimum development length for compression is going to be 200 millimeters. In tension, it was 300. And also it says the length calculated based on these 2 equations right here. In this case, I have to use again the greater of A and B. Now here it's 0.24 FY the epsilon psi r is what we call the confinement modification factor. So you calculate from equation A and B, and you take the larger one. Okay. Now, if I look at this confinement reinforcement, again, lambda, we're going to use it as 1. Here, reinforcement enclosed within 1, 2, 3, or 4. So if I have any one of these 4, I can use 0.71. Well, again, spiral is usually for columns, so if it's a spiral reinforcement, I can use 0.7. If I have a circular continuously wound tie with diameter of B more than 6 millimeter and pitch 100 millimeter, again, the pitch, I think I talked about it before, but I'm going to re-mention that when we talk about the columns. Number 3, 13 bars. Again, this 25.7, I'm going to mention that when we get into the columns, inshallah. Okay, but again, usually the confinement ratio is usually 1, except in cases where you have a spiral, we use 0.5. Now, there is a reduction factor that can be applied for both the compression and the tension, and this is where we multiply that development length by the required area of steel divided by provided. So if you remember when we did our flexural design, we got, let's say, an area of steel equal to 1500 centimeters square as an example. So when we go into the tables and collect and try to find the right diameter of the bar, and we usually use a number that's more than 1500 centimeters square, millimeters square, excuse me. Okay, so let's say if I used 1700 for instance, okay, then what I will do, I will take that required, the 1500, the one that I got from calculating the actual area of steel, divide that what I'm providing, which is, let's say, usually my 6,520 or 4,520, which is usually more than what I get from calculation. So this ratio is going to be less than 1. Then I can multiply that by the development length that we already got previously. Where it is not permitted to use that, where I have non-continuous supports, which is usually at the ends, location where anchorage is actually required, okay, which is usually at the critical sections. Bars are required to be continuous. Well, since they're continuous, then I cannot use that as well. If I have hooks, headed, mechanical, anchor deformed reinforcement, I cannot use that as well. The last two are related to seismic analysis, which we are not going to get into in this class. So let's actually, I know I've given you a lot, but hopefully these next examples will kind of clarify what I'm talking about. So let's start with example 1. So for the cross section shown, which is this one right here, it is simply supported, reinforced with 4 phi 25, confined with phi 10, so this is my phi 10 still up right here, spaced at 150 millimeters, so these phi 10 are spaced at 150 millimeters throughout. The beam is made from normal weight concrete, bars are not coated, F prime C is 30 megapascal, Fy here is 550. He wants the development length according to the table and the equation. Okay, so I'm going to use both to show you the differences between the two. All right. So let's start with the table. Like I said, we had 3 conditions, right, to use. First of all, I have 525, so now I have to look at the equation of number of 522 and larger. I'd like to calculate the spacing, the clear spacing between these bars right here. So this is my clear spacing, and that's going to be my B minus 2 times the cover, which is this 40, plus 5, which is my stirrup 10, minus 4 times 25 divided by the number of n minus 1, which was 3. So this is giving me a clear spacing of 33.33. Divide that by 25, so this is 1.33 diameter of the bar, which is larger than dB. So that's the first condition. Clear cover again is to the surface of the steel, so that's going to be my 40 plus 10, so that's 50 millimeters, which is 2 dB. I have stirrups every 150 millimeters, which means I'm covered by more than the code minimum. So I have all the requirements for the first conditions. Then development length is going to be Fy times, there's no zinc, it's not on the top, it's on the bottom. I have a grade 550, so I have to multiply by 115, divide by this factor 1.7 times 1, square root of 30, and it's giving me about 1.9 meters. Now, usually in projects, what we do, if we have, let's say, the same conditions everywhere, instead of doing that every time, I calculate the factor by dB, and then I says, okay, I'm going to use 75 dB for the whole project for bottom steel only. So if I have only 550 steel, I have all my reinforcement is more than 22. I'm maintaining all the space requirements. Then I'm just going to use 75 dB for the whole project. Okay, and that's what usually happens. Now we go to the other part, finding the equation. So now for that I have to determine what we call CB. So we said CB comes from two parts. One is the clear cover to the nearest surface. So if I take this one right here, which I'm going to call CB1, it's going to be my cover 40 plus phi 10 plus the center of the bar, which is 12.5, so this is going to be 62.5 in the horizontal direction. This is the one that I'm talking about. Now in the vertical direction, it's going to be 40 again plus 10 plus 12.5, because I'm maintaining the cover in both direction. So this is also 62.5. Now CB3, I said it's 1/2 the clear spacing between these two, center to center clear spacing, excuse me. So now I have the 33.33, which was the clear spacing that I calculated, added half of the diameter from both directions, so that will become 25. Divide that by 2, I have 29.2 millimeters. So since this is controlling, which means the splitting is going to be in the horizontal direction. Okay, so for that, the effective, what I call the effective ATR, are actually this leg here and this leg here. So I'm multiplying, I'm using 2 times the area of phi 10, which is 78.54 millimeters, and I'm getting 157.08. So KTR is equal 40 times 157, which is my ATR. Spacing, as I said, was constant, which is 150 times 4, and that's going to be 10.4, and which is more than 12.5. Now, so by that I can now calculate the CB plus KTR over dB. It's 1.59, which is less than 2.5. So with that, I can now calculate the development length. So development length is Fy, which is my 550, epsilon top, since this is bottom, so this is equal to 1. There is no epoxy, so this is 1. Size factor, since this is 25 more than 22, so this is also 1. Now the grade factor, since it's 550, I have to multiply this by 115. 1.1 goes down to 1.1. Lambda is 1. Square root of 30 times this, what we calculated. Sorry, this is 1.6 or 1.59, not 2. So by that, I'm getting 1.75 meters. So as you can see here, it is kind of a little bit less than the 1.9. So the other thing is, if splitting was controlled by the vertical direction, then in this case ATR will be equal to 4. Now, why is it 4? Because here I have, for each bar it is seeing 1 ATR. Okay, so this bar right here is preventing the crack from propagating. So it's seeing this once here, and it's seeing it here, and it's seeing it here, and it's seeing it here. Right? So that's why I'm using 4. But then if you notice, the number of bars are 4. So 4 by 4 would usually cancel out, and then if you just multiply it by ATR, then it's going to be 1. One more thing. So let's say if I added another hook right here, okay, and again splitting is controlled in that direction, then my ATR would be 1, 2, 3. Okay, so any lateral reinforcement that is working against the crack is going to be considered in my ATR calculation. Okay, let's do another one. In this example here, I have a beam column joint. Negative steel area required is 18.7 centimeters squared, and I'm providing 2,536. Thus, the provided area is 20.36 centimeters square. I'm using normal density concrete, F prime C28, FY 420. It says find the minimum distance LD at which the negative bars can be cut off based on development of the required steel area at the face of the column using the table or the equation. So again, the distance that I'm talking about is this distance. So how long can I maintain the 2,536? And I'm talking about the top one. I'm saying that stirrups are space 4 at 75, followed by constant 125 spacing in the region of the support. So meaning that this is my 125 over here. The drawing doesn't show it as such, but again, the region of the support, I'm using 125 millimeters. I'm going to do the same thing as we did with example B1. I'm going to calculate the spacing, and I found that to be 78 millimeter or 2.17 dB. Clear cover again is 50 millimeter, 1.39. For the top bar, again, it is also 2.28 dB. So all the requirements are met. Then I'm just using this equation straight forward. Here I have, since he wants me to cut the top bars, I'm using 1.3 factor because I have more than, I actually have 45 centimeters, which is more than 30, and this development length is 2.19 meters. Then I'm going to use another factor, reduction factor, which is 18. Again, this is the required divided by the provided, so I need 2 meters development length. If I'm going to use the equation, again here I'm going to find CB1, CB2, and CB3. Okay, CB1 again is the half the distance, which is 57. CB2 is again 40 plus 10, which is the side one, this here. The top is the 100, which is 55 minus 45. Again, CB1 controls, so the potential splitting will be in the horizontal direction. Here the spacing of the stirrups is 125. I'm developing 2 bars only, and then the ATR, again, I have 1 leg here and 1 leg here, so that's why I'm using 2. So this is getting 25.13. Calculating CBR, this is 2.28. Again, it's less than 2.5 and more than 1.5. Here I just want to mention the 1.5. Actually, for practical reasons, we usually do not use more than it's usually around 1.5, by the way, usually. Okay, that's from practical considerations. So now plugging that all into the development length equations, I'm getting 1.48. Multiply that by the reduction factor, so this is 1.4. So here you can see the use of while we want to use the more involved equation and KTR calculations, because it kind of reduced my development length about 30%, and that's something. Okay. Last example, and here I'm just gonna measure that for columns. Here I have a column reinforced with 8532, and they're gonna extend into the footing. Determine the development length needed for the bars to extend down in the footing. My normal weight is 30 megapascal and Fy is 420 megapascals. Since I have no information on the confinement ratio R, I'm just going to use that 1. 0.42 times 420 divided by 1 times square root of 30 times phi. It's giving me about 588, which is more than 200 millimeters. So this is the equation A, like I said. If I go to equation B, it's going to be 0.043 Fy. Again, I have no information on the confinement. I don't know if I have a spiral or not, times dB. So I'm just going to use it 1. And that's giving me 577. So the larger one is obviously the 580. So I'm going to use my compressive development length about 600 millimeter, which means I'm going to extend 60 centimeters into the footing. Okay, and that concludes this part of the development length. You guys stay safe and have a nice day.